In this video, we are going to study the modeling of throwing. Okay, so throwing motion, like as we could see from this picture, Kim Byung-hyun, the major leaguer, Korean major leaguer, we could see the sequential rotational motion of the body, like from the torso to the shoulder and the elbow and the wrist. There are some like a sequential delayed motions that could be observed. This delayed motion, sequential activation of multiple muscles are observed for many other throwing motions, like throwing the basketball, like from the knee extension, hip, shoulder, and the wrist, kind of sequential activations are observed. And same for the golf swing. For golf swing, we actually rotate the knee and waist and shoulder and the elbow, etc. So those sequential motions are pretty commonly observed motion for many of the players. Okay. So what has been known from the biomechanical analysis is those activations are mostly happen from proximal to distal. So proximal stands for whatever near to the body center, okay, to distal, which outward from the body center. So that's what we could observe here in the or mostly the other throwing motion. So what we could then ask for a question using human motion analysis technology to understand this sequential activation. Sometimes it's often, though I think the most important step to ask a good question for the good research, right? So also this chapter is also referred to the Alexander's paper, and then previously he sort of proposed that there should be combination for optimal touchdown angle and the velocity that will generate the maximum the best performance. And same for this one, how the sequential delay would affect the performance. So are there any optimal sequential delay exist? I think this is pretty smart and fun question. So after well-defined question, you have to set up the goal for the model analysis for that. So since we set it up the goal as there may be a optimal sequential delay would exist. Next step, what we could expect is maybe we'd better find the relationship between the delays as a function of ball velocity, and then see if there's any local or global minimum or maximum values. Okay, so I'm going to briefly go over what are the solution steps for throwing analysis. So similar to the previous human motion analysis, the very first step is to obtain the equations of motion. But the different thing here is, since we are working on the sequential activation, what that means is you have more than one joints, right? So you have a couple, like more than two joints that is activated first and second with the time delay tau. So either instead of having a point mass approach, we are going to have at least handle two masses or two joints. So that's the biggest differences. So assuming that the first muscle has been activated throughout the motion and the second one is initiated after delta t. So let's say there we have more variables than the point mass position, like a state variable like x1 and x2, etc. And those corresponding torques applied at that state is going to be something like starting with the t and applied after time delay, tau 1 and tau 2, etc. Okay, so once we obtain the equations of motion, the next step is we should integrate it up to a certain point. So here will be a release point, ball release point. So for the jump, that has been determined as a torque equals to 0 or leg has been straightened. But how about throwing then? Yeah, that's what we're going to talk about. Maybe either the torque at the joints turns out to be 0 or the arms or knees should be straightened. Maybe pretty similar constraints will be applied for that. Okay, and then with that variable time delay, we are going to examine the final bore energy or bore speed, and then examine if there is any optimality exist. Okay, any tau, the tau that generates the largest velocity, ball velocity. And with the results, we are going to judge if our proposal, the hypothesis has been proved or not, and those results make sense physically, and then we could also compare those results with the data and even examine if we could predict the motion. Okay, so to model this torque, joint torques, we could call those muscle modeling, the Hills model. And to the before that, we are going to make some assumptions about the muscle activation has a maximum, so A equals to 1. No dynamics for the A. And muscle 1 is activated throughout. So what that means is if the muscle 1 is activated and deactivated, and second one is activated, deactivated with the tau delay. No, the first one will just go over throughout the motion. That's what we we assumed here. And we are not going to include those tendon compliance. Okay, for the previous jump example, we examined that this one dominates most. And then among those contractile element, assuming that maybe the range of the motion change doesn't really affect the results, so force velocity relationship will be dominantly affect to the motion. That's what we assumed in the previous jump study. So we're going to also again use the same assumption here, like length change effect will be negligible and compared to the rapid speed change and its corresponding force variation of the muscle. Okay, so your muscle force will be again as a form of reciprocal function of joint theta, joint angle, angular velocity here and here. And we are going to use that as a force source of the equations of motion. Okay, let's examine how we could formulate the kinematics. So, so this is a simple schematics for the vertical throw. The vertical throw, you have a knee joint actuation and the elbow joint actuation, and configuration of the body postures are somewhat this way. However, to make this problem simple, let's just constrain all the motion happening in the vertical. So with respect to the center of mass, let's move on. Your arm movements are constrained in the vertical direction, okay, to make this problem simple. And we could set those model parameter based on the human observation measurement of the body length and height and so on. Those are the numbers what we have observed from the statistical analysis for the human body parameter values. And those angle between the elbows and knee joints will take the role for determining the joint torques. Okay. And state variables are there are two masses at the center of mass and the ball. So the distance from the vertical distance from the ground will be the two state variable in this equations of motion. So kinematics to describe the y of m, the center of mass, it's only depending on the angle for the knee, okay? And for the ball, it's gonna be angle for the knee plus angle of the elbow. So those are involved to describe the y of m, the ball height from the ground, and also can define the velocity by taking a derivative of them. Okay, how can we get the equations of motion? Let's draw a free body diagram. Okay, so since we are handling the sequential muscle activation, again, the knee joint torque is going to be activated first, and the elbow joint torque is going to be activated with the time delay tau. So assuming point mass and the massless leg, again, the problem turns out to be simple by be able to relating this force and torque relationship as a constraint for the massless leg. So your ground reaction force is going to be as a function of knee joint torques, okay? And that same for the arm. So the massless arm has a joint force at the shoulder is going to be a function of elbow torque, okay? And those forces are also applied to the capital mass M and the small ball mass M. And with this free body diagram, we could obtain the equations of motion for the time when the time is less than tau. Only the knee joint actuations occur. The only external force, by ground reaction force, and the gravity will generate the total body acceleration vertical, okay, which is going to be same as y small m double dot. When time equals greater than t naught plus tau, there are two activations applied, and then your motion for the whole body and the balls are different. So two muscle forces, I mean the forces from the muscle actuations and the gravity will affect the capital mass acceleration, while the elbow joint actuation and the gravity will affect for the small masses. So what we could have is the total like equations of motion for the vertical throw, like between this t region less than tau, you will have everything in terms of torque velocity relationship here, theta dot ni. And for a t equal greater than tau, you have capital mass dynamics involved with the capital ni angular velocity and the elbow angular velocity. And for the small mass, the ball mass, you only have a elbow angular velocity related force velocity actuations apply the force. I think there are missing, there are typos, there are gravity terms missed. Okay, for the simulation parameters, I can set the initial condition for the knee joint angle and the elbow angle with the zero angular velocity. And also I set it up, the parameters for the maximum joint torques depend based on the literature. So based on the literature, find a similar setup and then also make some assumptions for that. Okay, so integrate the equations up to takeoff. When does the takeoff occurs? The release occurs. Okay, so the foot leaves the ground when the leg straightened, similar to the jump case, and then also either the muscle angular velocity reaches to its maximum value. So whenever the knee joint torque turns out to be zero, same for the elbow. So the arms has been straightened or your elbow torque turns out to be zero, then you stop the integration and release the ball. The next step is you can examine the results, how your obtained ball velocity is going to be a function of tau, and then see if there's any optimality exist, and also interpret the results. Okay, so by looking at the results as a function of time, you have a plot for the energy level that the ball has gained as a function of tau. And then as you can see here, it seems like there is an optimal point exists, like a local global point exists here, right? So at this point, this ball will have a largest energy level. As you increase the mass of the ball, like up to the point like a 25% of your whole body mass, I'm not sure if you could even throw it. There is no optimality observed. So which does also make sense that if you have a really heavy ball, I mean, a concurrent muscle activation for the whole body will work. And there is no kind of delayed optimality will exist. And then your simulation optimality for the energy and corresponding tau have somewhat different, like a double-fold different from the real data. So different from the jump simulation, the throwing simulation shows sort of discrepancy, and you should think about what causes those errors. So what model simplification involved will contribute to that. So for example, instead of having the horizontal velocity, which should be a certain like a significant amount, we just assume that there's only vertical motions exist. So maybe the no horizontal velocity component will add an energy level. And something like there are more joint actuation, like instead of only the elbow, there are some spinning at the wrist, all those additional energy should be applied from that, and then it'll actually extend the time delay. So those are, we have to examine as a researcher, what are those simplified model parameters will affect the main results and the total values. And also you should examine by adding those parameters, is this optimality existence will still hold or disappear. Also, you should do some parameter study by changing the delta tau and how the result looks like, and then are these results interpretable. So for example, if you have a really small t, which means it's almost concurrently activated, your knee joint and elbow joint, what really happened is your elbow has been extended so quick. Okay, so before your total body has some gain some vertical velocity, you like a too quickly release the ball. Okay? So if you have a too large delta t, again, instead means your knee has been extended and then fully reach it before actually your elbow try to, provide the energy to the ball. So it's not efficient as well. So it's by looking at those two extreme cases, we could imagine that there must be some optimal delta t that will give us the best that can gain the best maximized velocity by knee joint upward motion and elbow joint upward motion. Okay, this is a brief review for vertical throw modeling analysis. So next time we are going to study the overarm throw analysis.